Hello students, I welcome you all to the lecture series of physics. As you know, we have started our chapter laws of motion, and till now we have discussed all the three laws of Newton. And we have established the fact that force is always required to change the state of motion either in rest or in motion or the direction of motion. I hope the idea is very clear to you. Now it's a turn to extend our discussion and see how you can solve some questions based on the Newton's second law and about application of all the three laws. And I am here representing some tips to solve some questions. So these are the problem solving techniques by applying Newton's law. So as per the first step, it says draw a neat and clean diagram of the system. As I just told you, whenever we are drawing the free body diagram of a system, it should be very neat. So it happens there, whenever we are drawing a free body diagram for a system, it should be very neat so that all the values of the forces are neatly seen and can be correctly put in the equations. So the first part we have discussed. Then isolate the object whose motion is being analyzed and draw a FBD for this object, and then find all the components of forces along the coordinate axis x and y axis respectively, and then apply Newton's second law. See, you can apply over here is that take the components of all the random forces in x or y coordinates and then compare the x coordinate force with the other x coordinate force. So that is the basis of solving questions in competitive examinations. So let's see some questions based on these techniques. So the first application we have, the first category is to find tension in a string in a very simple scenario. In this scenario, you can clearly see I have an object that is being hanged with the help of a string, and the string is being connected to the ceiling. Now the task is to find the tension in the string. Now to move further ahead, we can see this is capital M. Now I hope you remember the first step of FBD that says choose the system. Then the second point is draw the free body diagram of the system, that is mg, and then draw all the contact forces or identify the contact forces and draw them with their directions. Clearly you can see over here the string is pulling this object in the upward direction with the tension force T, and that can be labeled like this. Now the third and the most important point is choose the direction of motion. That says if the system is in equilibrium, then the net force on the system should be 0. Otherwise, if the system were moving, then I would enclose this in a box and move it downward or upward depending upon the question. We are going to see in the further question, but here the system is in equilibrium, and when the system is in equilibrium, what is going to happen? The net force on the system is 0, so simply tension is equal to m into g. I hope this is very clear to you. So ultimately what we have seen over here, when the system is stationary, the tension is equal to mg, and I hope the free body diagram which I have discussed over here is very clear to you. So let's move ahead and see the next case. For a uniform rope of mass ms, now what we have done is, initially the mass of the string was taken 0, but if in some question the string also has some mass ms, now what is going to happen? We know whenever there is a string with mass, tension at all the points will not remain same. So let's suppose a L length string having a mass ms is being hanging from the ceiling, and now the question is find the tension in the string at a certain distance x from the bottom, or we can say from the below. I hope this is clear. Now let's suppose the total mass is ms. So the mass of this element, if I draw the free body diagram of this section of the rope, let's suppose the mass of this section is small m. So the mass of the small m is taken. So first I can draw the weight of this object in the downward direction, and there would be a tension force that is appearing in this section being exerted by the upper part of the wire in the upward direction to keep this system in equilibrium. So what is going to happen? So this is the tension at x position. Now this whole system is in equilibrium, that's why Tx must be equal to mg, but the mass of the section of the rope which is hanging from this point is not known to us. So how we can find that? we can simply imply that this rope is having a uniform mass density. So the total mass is given, total length is given. By using the unitary method, we can find that for L length the mass is m, for a unit length mass is m by L, and for x length mass would be mx upon L, and this is the value of small m as per the question. So tension at x point is equal to capital M G upon L into x. I hope this expression is very clear to you. So ultimately what we have obtained over here is, if the system is stationary, then tension at a distance x from the lower end is equal to msgx by L. I hope this is pretty clear, and the idea and the concept of application free body diagram is very clear to you. So these are the two cases which we have discussed. Let's move ahead. The third case. Now we have a situation, platform is being placed on the ground with certain mass, and on the platform there is a block of mass capital M. Now here we can see that mass of the platform can be taken as MP. Now how can we draw the free body diagram of the block? Now this capital M, we have identified system. Now we know there should be a weight of the object which is acting in the downward direction. But if I ask you, that's all about the forces? No. There must be a force between M and the platform, because there is a contact of surface. Now whenever there is a contact of surface, there is an exchange of force. So if I can see, there is a force exerted by the platform on the capital M to be N, then what is going to happen? These two different forces, N from the platform, mg from the earth, these two forces are acting on the system, and clearly you can see the system is in equilibrium, and when the system is in equilibrium, the net force is 0, and since these two forces are opposite to each other, the net force must be 0, so N is equal to m into g. I hope this idea is very much clear to you. Now from here I can see, if I want to find out the free body diagram of the platform with respect to ground, what is going to happen? Now again, this is the platform, mass of the platform. Now we know first point is the weight of the platform, mpg. Now what would be the next thing? There are two surfaces which are in contact with the platform. One is with the block, one is with the ground. So ground would be exerting some normal reaction, and the block would also exert a contact force. Since the contact force exerted by the platform on the block was in upward direction, so the contact force exerted by capital M on this platform would be in downward direction, that is N. I hope you remember the expression from the previous case. So we have the N, and there is also a normal reaction from the ground. So these are the three forces which are acting on this platform. If I draw the free body diagram of the platform, and since the platform is also in equilibrium, I can simply write that the normal reaction from the ground is equal to the normal reaction from the block capital M plus mpg. And I hope you have understood the expression. Now from the previous case, you can see over here the value of N is equal to capital Mg. So we can substitute the value in the next case. So this we have like this: normal reaction from ground is equal to capital Mg plus capital M platform plus G. And I hope this expression is very clear to you. So the force exerted by the ground on the platform is actually the total weight of platform and capital M. And that should be the case. I hope this is very clear to you. So let's move to the fourth case, in which two blocks are connected by a light inextensible string as shown. Clearly you can see on a smooth surface, first most important thing is the surface is smooth, because in the case of friction also we are going to do the same kind of questions. On a smooth surface, these two blocks having mass m1 and m2 connected by a string are being pulled by a force F, and since the surface is smooth, the whole system is moving rightward with an acceleration A. Now the task is to find out the free body diagram and then solve the acceleration and also find the tension between the blocks. Now, if I draw the free body diagram of M1, what is going to happen? Clearly you can see over here, if I draw the free body diagram, M1 will have two forces. One is the M1G, that is weight of the object. Another is the N1, that is the reaction force by the ground on M1. And we have also a force of tension that is being provided by the string on the mass M1. I hope this free body diagram is very clear to you. Now if I talk about the mass M2, M2 will experience a force F towards right, tension towards left, N2 by the ground and M2G in the lower direction. I hope this would be pretty clear. Now if I ask you about the equilibrium of this system, the system equilibrium can be judged in two directions. Clearly you can see the whole system is just moving horizontally. So there is an equilibrium in y direction. So this N1 actually is equal to M1G. Here also this N2 is actually equal to M2G. And I hope you remember this condition. Now there is not any equilibrium in the horizontal direction because there is a motion. So what is going to happen? This tension force is responsible for pulling the object M1 in the right direction, and clearly you can see the whole setup is moving in this direction with certain acceleration A. So obviously this will also move with certain acceleration, this will move with same acceleration, and M1 will also move with the same acceleration. So what is going to happen? If I am going to apply the concept of Newton's second law in M1, I can clearly see that T should equal to M1 into A. I hope this equation number 1 is very clear to you. Now if I draw the Newton's second law for M2, I can clearly see the net force or the net motion of the system is towards right. So obviously this F would be greater than T. So what is going to happen? F minus T is equal to M2 into A. And this is equation number 2. And I can further solve these two equations to find out the acceleration. So what happened over here is I can also draw the free body diagram of the string, and clearly on the string there is a tension towards right, there is a tension towards left, and both the tensions are equal, and hence also the string is massless which is attached to the system. So there is no need to study the motion of the string. Now finally what we have got over here is that the acceleration of each block is force by M1 plus M2. Clearly you can see I can derive this expression over here. On reshuffling this expression, this F minus M1A is equal to M2A, and F is equal to M1 plus M2 into A, and which gives A as F divided by M1 plus M2, and this is the equation number 3 which we have got. And on substituting this value of acceleration over here, I can simply get tension as M1 into F divided by M1 plus M2. I hope this is very clear. So finally we have these two relations, and the acceleration and the tension expressions are very clear to you. So that's all in the segment. In the further segment we are going to see more cases in which we are going to solve the question based on the Newton's second law in much details.